Okay, hope this is working. Uh, not much is today. Okay, I'll give out the test at the end of the period and email a copy to Renee. It's not going to be due till next week, till Thursday. And the reason is that there are several topics in some courses I can stop before the chapter's over, but not in this one. We really need to have all these different techniques next to each other where you can figure out which one's supposed to be used and how to use it and so on. So what we're looking at, we're actually going to be doing some kind of special stuff here. There's a lot of little techniques in this first chapter on how to handle first order DEs, and some of them are very messy and technical, and I've said before that I hope you like that kind of stuff because you really do need it. Okay. So let me find my place here. We're looking at some special stuff in section 2.4. Not 2.4. 2.5. Sorry. Yeah. And I have to write everything. I don't have this other stuff prepared. I figured out the lecture, but I didn't type anything and added to the smartboard. Okay, so we're looking at expressions like this. So this is a true differential equation. It's not a derivative equation. And if we've already seen that it's going to be exact equation if the partial of m with respect to y is the same thing as partial of n with respect to x. And that turns out to be something that's pretty easy to solve, or at least pretty straightforward to solve if that's the case. However, this may not be exact. But that doesn't mean that we're left in the lurch with no way to solve it. There may be an integrating factor, which we've already seen one type of integrating factor with the linear ones. But there may be some integrating factor, okay, which would be a function of x and y. So that if you multiply both sides by it, if you multiply mu of xy times m, excuse me, looks pretty bad, dx plus this times n dy equals 0 is exact. Now, integrating factors are really important things, and a lot has been written about them. Books have been written on them, and techniques have. So we're just going to look at, hopefully, a case where it's not too awful, because they can get awful pretty fast. Okay. And they can be very hard to find. So here's a special case where we may be able to find them, and it's going to look strange. Okay. So we're going back to this equation right here. So I'm going to call this equation star. It wasn't exact, but if, okay, and this looks pretty bad, but just bear with me here. Take the partial of m with respect to y minus the partial of n with respect to x. Now, if these two things were equal, that would be 0. We'd have an exact equation. So these two things aren't equal, so that's not 0. If you take that and divide it by the function n, if this whole thing is a continuous function of x, then we can solve it. We can come up with an integrating factor. If we integrate this mess, with respect to x, and take e raised to that power, that becomes an integrating factor. So we'll compute that if it's, we'll compute partial of n with respect to y and n with respect to x anyway, just to see if they're exact. And if they aren't, if you subtract it and then divide by n and get a function of x, then we can come up with an integrating factor that's a function of x. And yeah, so this is like case 1. Case 2 is going to be the same sort of thing, only reversed and m instead of n. I can almost write it on the same board. Tell you what, I'll extend the page and write it down here. The second case is turn it around. If the partial of n with respect to x minus the partial of m with respect to y, so I just changed the order, divided by m in this case, if this is a continuous function of y, then, well, let's integrate that with respect to y. Take the integral of this thing, partial m x minus partial n, partial n. It's nx. And you see why I'm giving take-home exam, not asking to memorize a lot of these things. Okay. We integrate that, take e to that power, and that's going to be a function of y. Okay. And this is an integrating factor. There are several examples in this chapter where they have these special cases and special techniques, and I don't want to get too bogged down in them. But I do want to do one of these. Just because we can come up with a nice DE doesn't mean we can solve it, but sometimes you can if you're clever, or actually if somebody back in the 1700s was clever to come up with these ideas. Okay. So I'm going to do number 11 on page 69. It's very difficult to pick out examples to do in class because some of them that look like they're awful turn out to be nice, and some of them that look like they're nice turn out to be awful. And after I've written down something for 5 pages and decide I don't like that example, writing a lecture kind of wears me out, basically. Okay, so the DE we're looking at here is y squared plus 2xy dx plus, not plus, minus x squared dy. Okay, so m is the function that's in front of dx, so it's y squared plus 2xy. N is the function that's in front of dy, so it's negative x squared. We need to take the partial of these things, so the partial of m with respect to y. So look at this expression, and x is a constant just like 2 is, as far as we're concerned. So it's going to be 2y. And then 2xy, well, 2x is just the coefficient of y, so plus 2x. And the partial of n with respect to x is minus 2x. So if those two were the same, I'd have an exact equation. And we would then integrate m with respect to x and figure out whatever the constant function would have to be. But those aren't the same. Okay, so they're not exact. Now, I worked this out, so I know how it's going to work. So I found that if it took me, I didn't get this right the very first time. So, well, I mean, I didn't get it wrong. I just didn't know what was going to happen just by looking at it. This actually turns out to be a case 2 type of problem. As I said, I didn't know that until I worked on it and saw that case 1 didn't work. N with respect to x minus 2x minus 2y plus 2x. And m is y squared plus 2xy. This is minus 2x minus 2y minus 2x over that same thing. Okay, I'm actually going to, if you go ahead and start factoring the denominator, that's y times y plus 2x on top I have negative 4x and a minus 2y. If you factor a negative 2 out, you'll have 2x plus y. In the denominator, we have y times, well, y plus 2x is the same thing as 2x plus y. So those things cancel off, and we get, we're in the situation of number 2, where this is a continuous function of y. So, with that in mind, we take the integral of this, and fortunately it's simplified. And this is negative 2 log of y, so it's log of y to the minus 2, and we'll worry about constants. When you're doing an integrating factor, you don't mess with the constant there. It shows up when we're ready to do our final answer. Okay, so that's the log of y to the minus 2. And our integrating factor is function of y, and it's e to this power. Okay. So fortunately, things have worked out pretty simply so far. Let folks catch up a little bit. So the step next is to take this integrating factor and multiply the differential equation through by that. And what will happen is we'll have an exact equation. So let's do that. So go back up to our original and multiply everything times 1 over y squared. And if you'll allow me to just kind of do that here, so got to remember it. So I take the 1 over y squared and multiply everything by that. So when I multiply the first one by that, I get y squared times 1 over y squared, that's 1. And 2xy times 1 over y squared is plus 2x over y. That's dx. When I take the second one and multiply by 1 over y squared, I have a minus x squared over y squared dy. And 0 times 1 over y squared is 0. Now you can check this, but now this expression is exact. The derivative of the parenthesis term here in front of the dx is negative 2x over y squared. We take the partial with respect to y. The expression in front of dy, when you take the partial with respect to x, it's negative 2x over y squared. So this is exact. And I'll extend the page because we're about done. Okay. So you can verify that if you didn't remember what I said. So this means this is the derivative. Well, okay. So now what we have to do is we have to integrate this thing with respect to x. This gives us an x plus, this is going to be x squared over y, because we're integrating with respect to x, so that y is just a constant. And then we pick up some sort of constant term. I think we were calling that g of y or something. Because if we go backwards and differentiate with respect to x, everything that had a y would go away. Now this is our integral of m dx. I hesitate to write that down because that's not the same m as what we started with. But that's what in the process we're doing now. And so this is going to be my function of xy once we figure out what g of y is. So if we take the partial of that with respect to y, this is going to be the derivative of the x part's 0. The derivative of the rest of it is going to be minus x squared over y squared, because this is x squared y to the minus 1. Okay. And then I don't know what the derivative of g is. Okay. And since this is an exact equation, this expression should equal what we've been generally calling n, not the original n. So that's equal to, and things got negative x squared over y squared. So that means whatever g was, its derivative was 0, because there is no other term on this guy. There's no y term on that guy that we didn't have before. So that means g prime of y is a constant. I mean, g of y is a constant. Okay. So our answer should just be f of xy equals a constant. So it's going to be x plus x squared over y, and let's just put our constants on the right-hand side. It's a pretty simple looking little solution considering what it took to get there. Okay, well, the truth of the matter is I'm not entirely perfectly done yet. The book probably does a better job of explaining this, so they're a little bit more careful with it, but we multiplied by this guy up here. We multiplied through by 1 over y squared. And that meant that we're assuming that the y is not equal to 0. When you have an integrating factor, they point out there, and it may have gotten lost in all of this, when you multiply through by an integrating factor, you might actually be throwing an answer away. Okay. And that is true in this case. There are two possible answers. There's this one, or y equals 0. And if you look in the book, you'll see they write the thing. 3 little lines there. They don't say y equals 0. That means y is identically equal to 0. That means y is the constant functions. And you can go through here. So I'm not saying that. So y is the 0 function. And you can actually go through there and verify that y equals the 0 function, then that actually satisfies this differential equation we started with. Okay, so that was one of the special techniques things. If it's not exact, then these two things I had from the previous page, if you can use them, you can make it exact. Okay, you can't always use them, but that's just one of the situations here. Okay, I wanted to do in section 2.6, I want to talk about homogeneous equations, and I'm not going to do it quite like the book does. Even though when I prepared my notes, I set it up that way. What I'm going to do is equivalent to what the book says, but it seems to me to be a little easier to understand. So we're going to talk about homogeneous equations. And we'll actually see this word homogeneous used later on in a different way, but I don't think it's going to present any problem when we get there. Okay. First off, this is the new definition. A function of two variables, x, y, is homogeneous of degree n if, when you plug in, replace x with kx, replace y with ky. So just k just represents some constant here. If that's k to the n times f of xy. So homogeneous is kind of like every term in there is a degree n polynomial term. That would be a pretty good example. And we'll work one, when I work the DE, I'll have an example of that. Okay, well, so let's look at what a differential equation is going to be homogeneous. Place here. Okay. If, so we're having m of x, y, dx plus n of x, y, dy equals 0 is homogeneous. It's a homogeneous first order differential equation if m and n are homogeneous functions of the same order. Same degree, excuse me, not order. This is number 11, page 36. It's 3x squared minus y squared dx plus xy minus x cubed y to the minus 1 dy equals 0. So the function m, it's a function of x and y, is 3x squared y minus y squared. And the function n, it's a function of xy, is xy, x and y, xy minus x cubed y to the minus 1. Okay. Now, what we want to do is plug in a kx and a ky. And everything. So m of kx, ky is 3 times kx squared minus ky squared. So what we have in this one is 3k squared x squared minus k squared y squared. This is k squared times 3x squared minus y. So the first term is homogeneous of degree 2. Now we plug kx and a ky in for x and y in the second one. And if I can end up factoring out a k squared, then this is going to be what we call a homogeneous equation. So for the second one we do, and I know this looks like a pain, but this is really the easier of the two ways to do this problem. The way I'm doing it today and the way the book does it, this is actually the easier of the two. Okay. So replace x with kx, replace y with ky. And you see here kx, ky is going to be k squared times xy. In the second one, we're going to have a k cubed, x cubed, okay, k to the minus 1, y to the minus 1. But this is just k squared as well. So you can factor k squared out of these two terms. You have k squared times xy minus x cubed y to the minus 1. So it is degree 2 homogeneous. Okay. Now, the main difference is how the book tells us to verify this. And there's nothing wrong with theirs. And we're doing equivalent stuff here. Okay, it's just that his is a little bit harder to understand, a little harder to see. I think there's more chance of making algebra mistakes if you do it that way. Okay, so I haven't told you how to solve it yet, though. So let me start a new board and write the problem down again. Now, we're really not going to use the degree of homogeneity here. It's just that they are homogeneous. If one of them was a degree 2, the other has to be a degree 2 as well. All right, now what we do here is we solve by substituting. And what we solve is, the substitution is y equals v times x. And in the process of doing that, we're going to get an equation that's got v's and y's instead of x's and y's. Or in other words, so this is our substitution here. Every place there's a y, we're going to put a vx in there. So dy then, dy dx will be, it's going to be x times the derivative of v with respect to x. It's an ordinary derivative. You don't care here. Plus v times the derivative of x. So I'll just call that v. Okay. Okay, now this is actually going to give us a separable equation. And let me see, how do I want to do that? Okay. I actually kind of skipped a step here. This is not wrong, it just was a little bit early. I should have solved for dy dx to start with. So solve for dy dx. That means I'll get the dx over here. And now let's divide and do a few things here. Dy dx then is, and actually, okay, I went ahead and distributed this negative on these two terms. Okay. Now we put everything in. Okay. Instead of dy, I have x dv dx plus v. And over here, we substitute every place there's a y, we put in a vx. Leave myself enough space here. Oops. Plus v. Okay. So y is going to be vx. X dx. So I'll just write that as vx squared. Now x cubed, this is x cubed over y. Okay, that's what this term is there. So that becomes minus x squared over v. Okay. So let's see here. We need to simplify this. This is going to be a separable equation, but it's still got a little bit of separation to do here. we can factor on the right-hand side, I can factor an x squared out on top and on the bottom. And I'm left with then minus 3. Oh, have I lost my negative sign somewhere? To make sure. 3x squared. Let's kind of go. No, I didn't mess up a negative sign. Messed it up here. X squared times minus 3 plus v squared, or v squared minus 3, over x squared times v minus 1 over v. So the x squareds will cancel. And this can be simplified a little more if you multiply by v on the top and on the bottom. I don't like these compound fractions. V to the third minus 3v over v squared minus 1. Okay. Okay. All right, let's take another. Let's get this. We have. So I have x dv dx plus v equals this. So let's get this v over on this side. V cubed minus 3v over v squared plus 1, not minus 1. And this is I'm going to have to put these into one single fraction here. Because this is a separable equation. It doesn't look like it, but it really is. V cubed minus 3v minus v cubed plus v over v squared minus 1. Okay, because this term has to be multiplied by v squared minus 1 on top and on the bottom. That's where I get a v cubed minus v. And it's a negative in front of it. I made a mistake when I worked this out. Oops. Earlier. And this is working out to be a whole lot nicer than the mistake I made. Because the v cubes go away. And we have a 3v, a negative 3v, and a v. So we end up with a minus 2v over v squared minus 1 equals that. That is separable. I can get my v's on one side and my x's on the other. So if I multiply through by dx over x and v squared minus 1 over g, in other words, kind of cross, well, it's more than cross multiplying. I get extend it one more time. So when I would need to flip this side and multiply both sides by it. Ready to integrate just about. V squared over minus 2v. Okay, so that's what the left side is. V squared over 2v is cancels off, minus 1. Okay. So I integrate that. Integrate this. This is minus 1/4 v squared 1 log v is log x plus some constant. And better be careful. Are we done? Well, no. We're not done because we started out with x's and y's. So v was y over x. So replace every v with y over x and we're done. Minus 1/4 y squared over x squared plus 1/2 log y over x equals the log of x plus c. Never checked this in the back of the book, so let's see. Oh. This is what, page 76? This number 11? If it's number 11, I didn't get it right. Yeah, it's number 11. Have to go back and look at it. I messed up somewhere. Okay, log x plus c, that looks good, but x over that. I have to go back and see here. I don't know where I messed up. Since I really did get a separable equation, I have a feeling I didn't mess up before I got there. Well, we'll see. Okay, one more thing I wanted to do is I want to talk about Bernoulli equations. First, let's go back. We had these linear equations, which was dy dx plus some function of x times y equals some other function of x. And the way you solved that is you came up with an integrating factor, which was the integral of p of x, and then you take e raised to that power. That gave you some integrating factor. Multiplying by that gave you an exact derivative on the left side, and you could integrate straightforward that way. So Bernoulli equation is a version of that. Dy dx plus p of x times y equals some function of x times y to a power. Okay. And p is continuous. functions of x, and n is a real number. It doesn't have to be a whole number or an integer or something. It can be something weird like n 2/3 power or something like that. Now, if n equals 0 or n equals 1, this would be a linear equation. So, the way you solve this is we make a substitution. We let v equals y to the 1 minus n. Then in that case, dv dx is going to be 1 minus n times y to the minus n dy dx. So let's work one. I'm not going to have enough time to work one all the way through, but we can at least get it set up and see. Now, on a lot of these problems, the really long ones, I don't think the ones I have on the test are this bad, but on the really long ones, it would be like do the substitution, show that you get like on the previous problem, demonstrate that you get a separable dE, and then just stop. All right. Show how you'd make a substitution and show that would make the equation homogeneous, like the example before that, and stop. Okay. It's a lot easier to have one where you can set it up and demonstrate that it's the appropriate type, and then not worry about trying to find antiderivatives, because that can be a chore, as you've seen. I'll have to go back and figure out what mistake I made on the last one. This is number 23. It's dy dx equals, right, they don't quite have it in the right form yet, 2y over x minus x squared y squared. So it's not quite in the Bernoulli form. Now it is. So p of x, so I'll bring that 2y over x term over, the y to the first power. So p of x negative 2 over x, and over here q of x is negative x squared, and n equals 2. And what we're going to do is basically make this substitution, since this looks like a linear equation. When we make this substitution, we can fiddle around with it and make it into a linear equation and solve it that way. So we'll at least get this started here. So let's let's get this y squared term out of the way here. So let's multiply by y to the minus 2. So y to the minus 2 dy dx. Okay. Minus 2 over x y to the minus 1 equals negative x squared. Yeah. Okay. Now we do our substitution. So we let v be y to the 1 minus n, so that's y to the minus 1. Then dv, dy, dx, excuse me, derivative of v with respect to x is negative y to the minus 2 times dy dx, okay, which is almost what we've got here. So that means that negative dv dx is y to the minus 2 dy dx. So we can substitute in here. This is minus dv dx minus 2 over x, and this is v equals negative x squared because v was y to the minus 1. And now this is just about linear, except we got an awful lot of negative signs. So let's multiply everything through by negative 1. We have dv dx plus 2 over x times v equals x squared. This is a linear DE. And I'm going to write down P of x and Q of x again. Well, I don't really need Q of x. P of x, this is not the same one we had before. It's almost the same one, but not. It's 2 over x. So this is not this P. It's a brand new problem now, pretend. So, and the way we solve it, linear DE, is we integrate P of x. And the integral of 2 over x is going to be 2 times the log of x, which is the log of x squared. And the integrating factor is e to this integral. E to the log of x squared is, fortunately, just x squared. Multiply everything through by that. Everything through on this equation. Okay. Yeah, we can get done. And I guess extend the page one more time. So the integrating factor is x squared times dv dx plus, okay, when we take x squared, so we're multiplying this guy here. When we take x squared times 2 over x, that's going to give me 2xv equals x cubed. The left side is the derivative, is a perfect derivative of x squared v. So to get, we want to integrate the right side. X squared v is the integral of x cubed dx. Which is 1/4 x to the 4th plus c. So let's write that. We're virtually done here. X squared v is 1/4 x to the 4th plus c. And we would be done, except we started out with x's and y's. We need to end up with x's and y's. V is 1 over y. So So substitute back in, and I think we can actually solve for y in this case. Multiply both sides by y. Let's divide through. We're going to get x squared over 1/4 x to the 4th plus c equals y. So multiply both sides by y, and then divide by that 1/4 x to the 4th plus c. Okay, and let's see. Oh, I made a mistake, didn't I? I couldn't read my own writing. Got to go back. This is a minor, very minor mistake. This was an x squared. And when you multiply through by another x squared, you get an x to the 4th here. So everything that says so I should be integrating x to the 4th. This should be a 5th and a 5. So I think that's the only x squared over 1/5 x to the 5th plus a constant. Yeah, that's what I got. So just go through here and change these 4s to 5s. And the mistake I made was I couldn't read my own writing. Multiply everything by the integrating factor of x squared. It's x squared times that x squared, which should be x to the 4th. Okay, well, let's hand out a test here and say a few words about it. Okay, this is a test. This is a take-home test. So you're allowed to look at your book. You're allowed to look at your notes. You're allowed to look at anything I've put on Moodle. I have put some homework keys on Moodle. You're allowed to ask me questions. You're not allowed to look at any other book. You're not allowed to access any sort of website or anything for this. Okay. So what I suggest you kind of do is maybe you go back and make sure you've worked a lot of the homework and stuff before you start looking, because once you've looked at this test, you really aren't supposed to look at anything except what we're doing in class. Okay. Because you may accidentally, find one of these problems. You open up another book, you may accidentally find one all worked out. Okay. It's going to be due Thursday, October 5th. Which means what I'll do Tuesday is I'll clean some of this up. We've pretty much done everything. But Tuesday I'll clean some of this up and maybe work another example or two. And you can ask questions or so on. You need to make sure that you have the Euler thing, and probably, I don't think I asked you to do the direction field, but I have one here on there. And it never hurts. The direction field sometimes is a way to check an answer. But here you go. Let's see. And do I need to say anything else on problem 2? Okay, you've got not problem 2. It's problem 2 on the old test. It's problem 5. Okay. Determine if each one of these is such and such. Okay. So you need to say yes or no for about everything. One of these problems may be separable and homogeneous and linear and exact. Okay. You might have all 4. It might have none of them, too. But just show me what you did on there to make your decisions. Okay. Don't solve those. The ones on further down are the ones you solve. Okay. I don't have any idea where those number 5 are easy or not. Okay. So don't do that. So take a look at these and come up with any kind of questions you got. As I said, I'll do a little bit of review, clean up some of these, figure out where I messed up in that one problem, because it's probably something very simple. But as you see, it's easy to make mistakes. And I'll see you then.